Now we will discuss integration today. So we'll go over the fundamental theorem of calculus. So first version says that if f is Riemann integral with respect to some non-decreasing function alpha, and if f of x is defined to be to x f of t dt, then f of x is continuous. Capital F of x is continuous. And if small f of x is continuous, at x naught, then we have f dash of x naught is equal to f of x naught. So this is the first version of the fundamental theorem of calculus, connecting the integration and differentiation. And the second version is f is Riemann integrable and let and if there exists a function f such that integral such that capital F such that f prime is f, then integral a to b f of x dx f of b minus f of so let's solve some questions. So the first question is if f is a continuous function from R to R and capital F of x is defined as integral from a to x f of t dt. Is f of x is capital F of x is a continuous function and is f differential. So to answer this question, The question is capital F defined to be a to x f of t dt uh, is continuous. So because f is continuous, f is Riemann integrable. And by using the fundamental theorem of calculus, we have capital F to be um, continuous. And so that answers the first part. And then the question is F differentiable? Because F is continuous everywhere, say we are dealing only with the intervals A to B. F is differentiable, F is continuous everywhere in A to B. It follows again from the same theorem that capital F is differentiable in A to B. That's the first question. And the second question is, we say function is bounded variation if there exists some k, positive k, such that this successive sums, the differences are bounded by some constant. So, so the answer is yes, every function with a bounded variation is bounded and is Riemann integrable. So to see that uh, if f is bounded variation, then f can be represented as a difference of two monotonically increasing functions. So f1 and f2 are non-decreasing. And now any monotonically increasing function can have only countable number of discontinuities. Uh, and so that means f1 is integrable. And similarly, f2 is also integrable. By linearity, f1 minus f2 is also integrable. And thus the function, any function f with a bounded variation is integrable. Third question. Now, F maps or closed interval B to R as a Riemann integral. And for any ST, we cannot be defining F as Ft to be um, S2x, F of u du, and F of t is t2x. T. Then for all x in A to B, the function f of s minus ft is a constant function. So this is easy to see if we say we assume that there exists a function g dash is equal to f. Now fs what from s to x of t dt f of t e to x f of t dt. We're using the second fundamental theorem of calculus. When we have this can be written as g of x, g of x. Similarly, this can be written as and CFS of x t of x. Simply g of t as g of s. Let's go to another question. So as a function f mapping from closed A to B to R, we can be the sequence of partitions from A to B such that the upper sum where the partitions are taken over k square and the lower sum of the partitions are taken over k cube is 0. Then there is this. So the this thing Question is if limit k tends to infinity, a sum of k squared f minus lower sum of bk cubed f. So the upper sums for any partition, this is always true. U of v1 comma f is greater than or equal to that of v2 comma f. This is true for any partition. Now, as the partitions are getting defined, as k is increasing, we have u of v k square comma f is than u of v k square comma f, and so on. As k1 is less than k2 is less than s1, and this is a decreasing sequence, and its limit will converge to um, its limit will converge to the supreme. So infinity. For all partitions. And similarly, because of the negative sign, this thing goes to this supreme partitions. Become f. Now this is going to 0. This implies that this is integral. So now there is a function f that is mapping from A to B to R, and there's another function f. C is positive, and it's mapping by shifting and scaling the original integral. And f of c dx is defined to be f of c expressed. So the function is scaled and mapped for all x belongs to this a minus t c to a minus t. So question is if f is Riemann integrable on a b, if FC is identical ST by C and ST by C for all C positive and T belongs to that. So question is we have defined a function f cx plus t. Originally, f is defined from a b to r. Now, after this, the function is shifted from a minus t by c. The interval is shifted from minus c minus t over c. So the question is, f is remain integrable on AB if finally f of x t is remain integrable on AB. So assume that this is true and substitute t0 and c is equal to 1. We get this. Now assume that f is Riemann integrable on AB. Then consider any point. Then consider this interval and the function f of 6 plus t. Can be easily seen that the values of this interval can be mapped to the values of this interval, and accordingly the function takes the values elicited from this interval as f was taking on a to b. So this implies that f of c plus t is ring because f is the amount interval. For a to b, this is the function, and after shifting and scaling city greater than 1, the function will be shifted and squeezed. Minus t by c. B minus t by c. So now given a function f mapping from closed a b to r as an analytic development, I want this function f prime mapping from the closed comma b to r as the negative of f of a plus b minus x. Which of the following is fat is Riemann integrable like both are equal, and fat is Riemann integrable. This is true. F is Riemann integrable and it be f hat is 0. Fat is not a Riemann integrable. So if we consider it to be f of t dt, let's consider a change of variables. So you substitute t is equal to plus b minus x. Then at a integral become b, at b integral become a, and f of x b minus x dt will be minus of x. And once we flip the sign with the upper and lower limits, we have only we have f of a comma b mapping to r as a Riemann integrable function. Consider following statements. If there exists a row such that mod f of x is greater than O, and for all experiment, then 1 over f is Riemann integral. This is true because then 1 over f of x is bounded by 1 over rho. And in the second case, we are given g of x as 1 over f of x is not 0. And in the second case, this is not true because f of x can be considered to be x. But then this is not integrable 1 over x at 0. So 1 is true, 2 is false. So we give an example of a function where which is continuous, but the derivative is not continuous. Square of x. This function at x equal to 0 tends to 0. And say take f dash of x is 2x times x minus cos of 1 over x. Now here f dash of 0 and 0, we encounter cos 1 by x, which oscillates between um, minus 1 by 1 around 0. But then if we compute f of t by definition, the derivative get this to be square sine of 1 over t by t. T sine t square. And this, as t tends to be, this is very close to 0 because this is less than a bond. This is less than equal to t.